Hi guys, my name is IBM and I'm here to solve October-November 2023 papers, and I'm now solving paper 2-3 or component 2-3, and without wasting time I would like to take you to the question papers. So here we have our question paper. So it is October-November 2023. What's wrong with my pen? Okay, so you can download the question paper October-November 2023. So I'll not go through the instructions. We now know the instructions. You can read through the instructions and check out the constants. I'll go straight to the first question. The table 1.1 lists some physical quantities. Complete the table by placing a tick next to the scalar quantity. Of course, we know acceleration is a vector, charge is a scalar, momentum is a vector, power is a scalar, up thrust, this one is a force. So it is a vector quantity. So it is only charge and power which are scalar quantities, because up thrust is a force, which is a vector quantity. Okay. A uniform cylinder has diameter d, length L, mass m. The density of the cylinder is given as that. Table shows the data obtained from an experiment to determine the density of the cylinder. They give us quantities and measurements, and they want us to fill in the percentage uncertainties. Okay, write your answers in the table. So for the first one, percentage uncertainty in D, remember percentage uncertainty is the absolute over the true value times 100. So for D, it is going to be 0.1 divided by 26.2. Then I multiply this by 100. So this is going to be 0.1 divided by 26.2 times 100. That is 0.3. Since what was given here is to one significant figure, so I'll round off this to one significant figure. So I'll write here 0.4. Then for the other one, I'll just put in the calculator 1 divided by 162 times 100, which is 0.6. I'm just maintaining the same number of significant figures here. Okay. Then calculate the density of the cylinder. Of course, they have given us the formula here, 4m over pi d squared times L. So I'll just substitute in. So density is equal to 4 times m. M is 27.247. I divide by 1,000, that is 0.247. To change it to kilograms, divide by pi. Then the diameter is 26.2 divided by 1,000, because it's in millimeters. I'll simply say 26.2 times 10 to the power of minus 3, but this is squared, times L. L is 162 millimeters, which is 162 divided by 1,000, that is 0.162. To change it to meters, so I'll just check my calculator. 4 times 0.247 divided by, I'll open two brackets. Okay, divide by 0.162 times pi. I'll open another bracket, 26.2 exponent minus 3. Close this bracket and close the outer bracket. So I'm getting 2828, or 2.83 times 10 to the power of 3. So that is 2.83 times 10 to the power of 3. Then percentage uncertainty, since the density is equal to 4m over pi d squared L, I'll ignore 4 and pi because they are constants. So it means the percentage uncertainty in density will be equal to the percentage uncertainty in m plus, because d is squared, we shall multiply 2 the power by the percentage uncertainty in d, then plus the percentage uncertainty in L. So in m, From our table, M is 0.4, L is 0.6, D is 0.4. So I'll simply say M, which is 0.4, plus 2 times 0.4, plus L, which is 0.6. So this is 0.4 plus 0.8 plus 0.6, which is 1.8. A ball on horizontal ground is kicked towards a vertical wall. The figure shows the path of the ball. Okay, this is projectiles. The ball has an initial velocity u at an angle of 38 degrees to the ground. So that means if we resolve u to the horizontal, it's going to be u cos of 38. If I resolve u to the vertical, it is going to be u sine of 38 degrees. Okay, the horizontal component UH of the initial velocity of the ball is 9.5 meters per second. Show that the time t for the ball to reach the wall is 0.95 seconds. So I will use S equals to UT plus a half AT squared. I'm going to consider horizontal motion. And if I consider horizontal motion, remember acceleration in the horizontal is 0 because there is no force acting in the horizontal. So this part here becomes 0. S in the horizontal is 9.0. Initial velocity in the horizontal has been given as 9.5, then times t. So t is going to be equal to 9.0 divided by 9.5. So 9 divided by 9.5, that is 0.947. 0.947 or approximately 0.95 seconds as required. Then calculate the vertical component UH. So of course we have seen that in the horizontal, U in the horizontal is 9.5, which is the same as U cos of 38. U in the vertical is not known. I'll call it U V, but it's going to be U sine 38. So I will divide the two equations. So I have U V over 9.5 is equal to U sine of 38 divided by U cos of 38. So U cancels. So U, the vertical, is going to be tan of 38 multiplied by 9.5. So I have 9.5 tan of 38, which is 7.42. So this is 7.42. So the answer here is going to be 7.42 to three significant figures. Then determine H. So H is in the vertical, so I'll consider vertical motion. And I'll use S equals to UT plus a half AT squared. S in the vertical is H. Initial velocity in the vertical, we have got it as 7.42. Of course, time is a scalar quantity, so the time is the same, which we got as 0.95. Because it's moving in the vertical, acceleration is negative g. So this will become minus a half times 9.81, then times 0.95 squared. So 7.42 times 0.95 minus open brackets 0.5 times 9.81 times 0.95 squared. So this is 2.62. So that is H. Then the speed of the ball just after striking the wall is less than its speed just before striking the wall. The speed of the ball just after is less than before. That means there has been loss in kinetic energy. Therefore, the collision is inelastic. State what this indicates about the nature of the collision of the ball with the wall. So we can simply say the collision is inelastic. The collision is inelastic because kinetic energy is not conserved. The collision is inelastic because kinetic energy is not conserved. As simple as that. Question number 3. State the conditions for the system to be in equilibrium. Of course, these are very easy conditions. Number 1, the resultant force should be 0. Resultant force in any direction. Resultant force in any direction is 0. The other one is about momentum. The resultant resultant moment or resultant torque. Resultant moment or resultant torque about any point is 0. And the figure shows an airship in flight. The airship is propelled by identical fans that can be angled to control the motion of the airship. The upthrust on the airship is 93000 newtons. The density of the surrounding air is 1.2. Capture the volume of air by the airship. So upthrust is equal to the weight, which is mg, which is going to be density times volume, then times g. So we want the volume. So the upthrust, density times volume times g is equal to the upthrust force. So the volume is going to be the upthrust, which is 93000 divided by density is 1.2 times g, which is 9.81. So 93000 divided by 1.2 times 9.81. So that is 7,900 meters cubed. When fully loaded, the weight of the airship is greater than the upthrust. When fully loaded, the weight of the airship is greater than the upthrust. To maintain horizontal flight, that is equilibrium, the fans provide a total vertical force of 3 times 10 power 3 newtons upwards on the airship. Calculate the mass of the airship. So if there is still horizontal flight, there is the resultant force in the vertical should be 0. In this case, the weight downwards should be equal to the upthrust plus the force from the fans. So the weight of the airship is the mass of the airship times g, which should be equal to the upthrust, that is 93,000, plus the force from the fans, which is 3 times 10 to the power 3, which is 3,000. So it means the mass of the airship is going to be 93,000 plus 3,000 divided by g, which is 9.81. So I'll just say 93,000 plus 3,000 divided by 9.81. So this gives me 9785 or 86. 9786 kilograms or 9800 kilograms. At a certain time, the airship will be stationary. The airship will be stationary. The thrust force exerted by a fan on the airship is 2,800 newtons, just one fan. To produce this force, a mass of 64 kilograms of air is propelled through the blades of the fan in a time of 0.5 seconds. Assume that this air is initially stationary. That means initial velocity of the air is 0. Calculate the change in momentum. So we know that force is equal to the rate of change in momentum. So this means the change in momentum is going to be force times the time. So the force is 2,800 newtons and the time is 0.50. So it is just a half of that. Half of 2,800 is 1,400. That is the change in momentum. Then the speed of the air as it leaves the fan. So remember that change in momentum is going to be mass times the change in V. So the change in momentum is 1,400. The mass is 64 kilograms. Then the velocity is V minus 0. So we just divide to find V. So 1,400 divided by 64. So that is 21.9. 21.9. So I can write 22 approximately to two significant figures. Then total kinetic energy. So we know that kinetic energy is equal to a half mv squared. This is going to be a half times the mass of the air, which is 64, and the speed is, I'll use 21.9, but this is squared. So I have 0.5 times 64 times 21.9 squared. So that is 15,347.52, which is approximately 15,000. So approximately 15,000 to two significant figures. Okay, that was an easy question. The figure shows the variation with extension X of the tensile force F for two wires G and H made from the same material. This is very important. Same material, they most likely have the same Young modulus. The elastic limit has not been exceeded for G or H. For the line, state what is represented by the gradient. Of course, F is equal to Kx. We have F against X, so it is the spring constant. Is that a spring? The figure shows the variation with extension X of the tensile force for two wires. I don't want to say spring constant, but I'll just say spring constant or the wire constant. But let me say spring constant or the wire constant. Explain why the area under the line represents the elastic potential energy of the wire. Of course, the work done in stretching the wire is the elastic potential energy, and the work done is actually the area under that graph. So the area represents the work done to extend the wire. The area, of course, the work done in stretching the wire, and yet the work done to extend the wire is the elastic potential energy, and the work done to extend or to stretch the wire is equal to the elastic potential energy. So because the area is the work done stretching the wire, and yet the work done is the elastic potential energy, so it means the area will be equal to the elastic potential energy. As simple as that. Then wires G and H are joined together end to end, so it's like they are going to be in series. They are going to be in series. A block of weight at 0 Newton is attached to the end of the wire as shown in the figure. Use the figure 4.1, which is the graph, to determine the extension xg and the extension xh. Okay, let's check here. The load added is 2.0 Newton, so they experience the same load. So 2.0 Newtons is here. This gives us this reading for wire H, and I think this is 0.29. And this gives us this reading for wire G, which I think is 0.39. So G is 0.39, H is 0.29. So we have 0.39 and we have 0.29. Then calculate the total elastic potential energy. So remember, elastic potential energy is a half times F times X. Or you can use a half kx squared, but I will use a half fx, or which is the same as the area under the graph. So let's start with G. For wire G, the elastic potential energy is going to be a half. F was 2.0 because we are considering a weight of 2 newtons, so it is 2.0 times the extension is 0.39 millimeters, so it is 0.39 times 10 to the power of negative 3. And then for wire H, the elastic potential energy is going to be a half times the weight, which is 2.0, times the extension, which is 0.29 times 10 to the power of minus 3. So the total elastic potential energy is going to be the sum of these two. So it will be a half times 2.0 into brackets 0.39 times 10 to the power of minus 3 plus 0.29 times 10 to the power of minus 3. So I'll just check this 0.39 exponent minus 3 plus 0.29 exponent minus 3, then times 2, divide by 2. So I have 6.8 times 10 to the power of 4 minus 4, 6.8 times 10 to the power of negative 4. The original length of the wire G is L and the original length of wire H is 1.5 L. Calculate the ratio cross-sectional area of wire G over cross-sectional area of wire H. So since they are made from the same material, the Young modulus is the same. Young modulus is equal to F L naught over AX. This E is not energy, it is Young modulus. But Young modulus is the same. So I would say for wire G, its Young modulus, F is the same. They have the same length, which is L. Let's say the cross-sectional area of G is AG times its extension we have seen is 0.39 in millimeters. Should be equal to the Young modulus of H, which is F is the same, but the length is 1.5 L. Its cross-sectional area is AH, and its extension is 0.29. So I'll cross out some of these for clarity. F cancels, L cancels. So I want AG over AH, so I'll just cross multiply. So I'll bring 0.29 to the left, divide by 0.39, should be equal to, I take AG up, so it will be AG over AH, but there's 1.5 up there, which I'll bring at the bottom here, 1.5. So just press my calculator, 0.29 divided by open brackets 0.39 times 1.5. So that is 0.496. So the ratio is 0.496 or 0.50. Okay, that is all. Question number 5 is waves. 2-point sources A and B produce coherent electromagnetic waves. The waves from A and B are emitted in phase. They are emitted in phase, so that means that the phase difference between the sources initially is 0. The lines on the figure represent wavefronts. All the points on a wave are in phase. On the figure, mark with a cross the position of an interference maximum. Of course, for interference maximum, a crest must be meeting with a crest. So we just look for any point where the solid lines are meeting. I'll say, let me just, because I want enough space, I'll put a cross here. And I say label this Y. So this is Y. So this point here is Y. Any point where the lines are crossing, the solid lines are crossing, that is maximum. A crest is meeting a crest. Then the position of an interference minimum, this is destructive interference. Destructive interference occurs when a crest meets a trough. So between every two crests, there must be a trough. So if a crest meets a trough, there will be destructive interference. So between two crests, there must be a trough. So I'm going to just choose, say, between these two. So when I draw a line in the middle of these two, this line is going to represent a trough. So somewhere in between, where a crest is meeting with a trough, that is going to be point Z. So this is going to be point Z. I'm going to remove the dotted line because this is just showing you that is supposed to be there's a trough in between. So that is going to be point Z. You choose any point between the two crests where a crest is just crossing the center between two crests. That could be Z. Z could be this point, Z could be this point here, it could be this point, could be this point, could be this point, just in the middle, where a crest meets a trough. That is going to be Z. So this is I've chosen that. You can choose any point where a crest crosses the center between two other crests. Then the waves in air have a wavelength of 2.9 times 10 to the power of minus 5. An interference pattern is detected along a line parallel to AB and a perpendicular distance 140 meters from AB. The spacing between adjacent interference maxima is 1.2. So this is going to be D. Spacing between maxima, that is X, and this is the wavelength. So these are two sources, so it's like a double slit. So for double slit, lambda is equal to AX divided by D. When I make A the subject, A is going to be lambda D divided by X. Now I substitute. The wavelength is 2.9 times 10 to the power of minus 5, then times D, which is 140, divided by X, which is 1.2 times 10 to the power of minus 2 to change it to meters. So I have 140 times 2.9 exponent minus 5 divided by 1.2 exponent minus 2. So that is 0.3383 recurring, or I can say, I'll just say 0.338 meters. State the principal region of the electromagnetic spectrum to which the waves belong. We just look at the wavelength. The wavelength is 2.9 times 10 to the power of minus 5. So if we look at the electromagnetic spectrum, Reed's mother is visiting Uncle Xavier's garden. Here we have the visible range, which is 7 times 10 to the power of minus 7 meters. And the other side, it is 4 times 10 to the power of minus 7 meters, where this is red and this is violet. So 2.9 times 10 to the power of minus 5 must be on this side of the visible spectrum. When I add a plus 2 on the power of red, I get minus 5. So that means this is going to be infrared. When I add plus 2 on red, which is 7 times 10 to the power of minus 7, I get the power of minus 5. So this is automatically going to be infrared. So that is infrared, just before red. Okay, next is still waves. A train travels at constant speed along a straight horizontal track towards an observer standing adjacent to the track. So it is towards an observer. The train sounds its horn continuously as it approaches the observer. The horn emits a sound of constant frequency 251 Hz. The frequency of sound heard by the observer is 291 Hz. The speed of sound is 340. Actually, the speed of the train. So since it is towards, the frequency is higher. And if the frequency is higher, we know that F naught is going to be V divided by V minus Vs, then times the frequency of the source. That is for high frequency. If it was moving away, it would be plus. So if I substitute, I have 290, sorry, it's not 290, sorry about that. So I'm going to divide F naught by Fs, so that is 291 divided by um, Fs, which is 251, should be equal to V, which is 340, divided by 340 minus Vs. So I will just cross multiply. So I have that 340 minus Vs is going to be 340 times 251 divided by 291. So if I want Vs, I make Vs the subject. So Vs is going to be 340 minus 340 times 251 divided by 291. You can do any algebra that you can. 340 times 251 divided by 291. Then I will say 340 minus the answer, which is 47.9. So this is 47.9. Let me check it again. 340 times 251 divided by 291. Then I'll say 340 minus the answer. So it is 46 point. It is 46.7, or approximately 47. Approximately 47 meters per second. Okay. The train approaches and then passes the observer. The intensity I of the sound heard by the observer varies with the distance d of the horn from the observer. The horn is at a distance x naught from the observer. The intensity I of the sound heard is I naught. So the intensity of the sound heard is I naught. And the amplitude A of the sound wave at the observer is A naught. So the amplitude I is A naught, the intensity is I naught. Okay. The figure shows the variation of d of I as the train moves away from the observer. Then state the relationship between amplitude and intensity. So we know that intensity I is directly proportional to amplitude squared. Then on the figure, sketch the variation. On the figure, sketch the variation with d of A, dx naught of A naught. So since I is directly proportional to amplitude squared, then it means um, A is directly proportional to I squared. I mean square root of I. A is directly proportional to the square root of I. Okay, so that is now going to be a straight line. You can check. A is directly proportional to the square root of I. If I is 1, A is going to be constant times 1. That is the point. Remember, I'm saying A is equal to a constant times the root of I. So if I is 1, A is going to be a constant times 1, which is this point here. Of course, the constant depends on whatever you want to choose. Okay. Then if I'm going to choose another point, I'll just choose a few points. Suppose I take this point here. Okay, I'll take this point here. Suppose I is 0.6. The root of 0.6, root of 0.6 is 0.77. So 0.77 for amplitude. So the scale here is 0.02. So 0.62646667 is somewhere here. It's approximately 0.67 is approximately here. Then I will check another point such as, let me check this one here. That is 2.8. I is 0.12345, 0.25. So the root of 0.25, that is a half, 0.5. So at 2.8, it should be 0.5, which is in the center here. At 2.8, no, this is not, this was 0.3, not 0.25. This is 0.3. So it is root of 0.3, which is 0.55. Okay. So I'll rub off this 0.55. So 2.8 is 0.55. So 1, 2, 3, 4, 5. That is 0.5. Then when I add two boxes, 0.52, 54, 55 is somewhere here. Then we have at this point here, let me just look at the last point at 4. At 4 here we have 1, 2, 3. That is 0.06. The root of 0.06, root of 0.06, that is 0.24, approximately 0.25. So we have 1, 2, this is 0.2224, 25 is approximately here. I need to check this again. Root of 0.3, 0.5. Okay. 1, 2, 3, 4, 5. That is 0.5, 5, 2, 5, 4, 5, 5. Okay. So I have those points and I have to sketch a graph. I have to check if they give me a straight line. Why do I feel I have sketched 1 point wrong? 0.6. The second one is 0.6. Root of 0.6. 0.7. Oh, yeah, this one is wrong. 0.7 is here. 7.2, 7.6, 7.8. So it is somewhere here. Okay, so I'm plotting the points. I'm plotting 1.0 against 1.0. Then I've plotted 1.9 against 1.9 against 0.77. Then I've checked 2.8 against 0.55 or 54. Then I've plotted 4 against 0.25, which is approximately 0.24. So this is going to be a straight line anyway. A is directly proportional to the root of I. That is supposed to be a straight line, so it should be a straight line here. And you have to adjust this line. So you can draw a better line, but this line is touching here. That is at 0.244 or 0.25 approximately. So it is supposed to be a straight line anyway. And notice how I've arrived at those values. I said if we know that A is equal to K times root of I, then K is a constant, so it applies to both. So I just consider the varying values, these ones here, and I plot the graph, which is going to be a straight line. So it should be a graph, a straight line with a negative gradient, which goes through, most importantly, this point here and this point here. As simple as that. If you want, you can just check the first, if you know the first point and the last point, you just draw a straight line. Okay, I laid much on that. State Ohm's law. So Ohm's law states that at constant temperature, at constant temperature, at constant temperature, the current through a conductor is directly proportional. Is directly proportional to the PD. Is directly proportional to the potential difference across the conductor. So at constant temperature, as long as the temperature does not change, the current is directly proportional to the PD. Okay, we have a battery EMF 6.5, negligible internal resistance C is connected in a circuit to a uniform resistance wire, voltmeter, a fixed resistor, and a switch as shown. The wire has a resistance of 18 ohms. The length of the wire is 0.94 meters. The cross-section area is 7.2. Then calculate the resistivity. So we know that resistance is equal to rho L divided by cross-sectional area. So resistivity is going to be equal to, I make rho the subject, so it is resistance, which is 18 ohms. Cross-sectional area is 7.2 times 10 to the power minus 8 divided by L. What is the length? Is 0.94. So I'll just press my calculator. 18 7.2 exponent minus 8 divided by 0.94. So that is 1.38. 1.38 by 10 to the power of minus 6. Then the switch is open, state the reading on the voltmeter. Let's see. If the switch is open, then the reading of the voltmeter is the PD across this part of the wire. But they said S is positioned halfway. That means the PD, which is the PD of 6, the EMF is divided equally in the wire here. Since S is halfway, so the PD across this is 3.1 and the PD for the remaining part is 3.1. So I'm saying the PD is divided into 2. So the EMF is divided into 2, so it is 6.2 divided by 2, that is 3.1. Then the switch is now closed. The switch is now closed means we have two resistors in parallel. If the switch is now closed, this resistance is in parallel with this. And whenever we have resistances in parallel, total resistance decreases. So total resistance in the circuit decreases. And if total resistance in the circuit decreases, even the resistance of this part is also going to be smaller. So the PD across this part decreases. So state whether there is an increase, decrease, or no change to the current in the battery. So I've already said total resistance decreases. And if from I is equal to V over R, or I is equal to the EMF over R, since the EMF is constant and the resistance has decreased, the current in the battery increases. So this one increases. Then the voltmeter reading. The voltmeter reading is actually the PD across the PD in the parallel combination. Since uh, since the current in the battery has increased, it means the PD for this part here becomes higher. And by conservation, the PD here will go beyond 3.1. So by conservation of energy, the PD here will go to less than 3.1, and yet the PD across here will be the EMF, the reading of the voltmeter, or the PD across the fixed resistor. So automatically, the reading of the voltmeter decreases. It decreases. An increase in current will make the PD across the other part, which is directly connected to the battery, to have a high PD. By conservation of energy, the PD across the parallel combination becomes smaller, so it decreases. The switch remains closed. The slider S is moved along the resistance wire so that the voltmeter reading is 3.1 volts. Remember, it had decreased. The voltmeter, the PD here had gone below 3.1. So because PD is directly proportional to length, the PD is going to be directly proportional to length. And to take it back, to increase it back to 3.1, we must increase the length. We must move S to the right-hand side. Okay. So let's see the question. On the figure 7.1, draw a cross on the resistance wire to show a possible new position of the slider. So the slider must be moved to the right-hand side. So I'll put an X somewhere here. It is increased back to 3.1. I can't take it to, I cannot bring it here, because when I bring it here, it means the PD goes to 6.2, which is the EMF. So I can't bring it here. But since I want to restore it to 3.1, then I'll put a point somewhere here, just on the right-hand side of the initial position for S. Then the circuit in B is altered by changing the battery for one of the different EMF. The switch is open, so that means the fixed resistor is out. The student records the following data: the current, that is I, mean drift speed, that is V, number density of charge carriers, that is small n. Determine the charge Q of a charge carrier in the wire suggested by this data. So know that current is equal to A V N times Q. So Q will be equal to the current, which is 0.93, divided by area, which is, I think they gave us the area. It was, what was the area? The area is 7.2 times 10 to the power of minus 8. So that is 7.2 times 10 to the power of minus 8, then times V, drift speed is 1.3 times 10 to the power of minus 3, then times N, which is 9.0 times 10 to the power of 28. So I'll just check my calculator. I'll start from the denominator. 7.2 exponent minus 8 times 1.3 exponent minus 3 times 9 exponent 28. So I'll get 0.93 divided by the answer. So I'm getting 1.10 times 10 to the power of minus 19. This is less than the charge of an electron because the minimum charge is supposed to be 1.6. So that means there is a problem with data. With reference to the value of Q, explain why data recorded by the student cannot be correct. It can't really be correct because we know that charge cannot be below. Charge cannot be below 1.6 times 10 to the power of minus 19 coulombs. So the data is not correct. So the data recorded cannot be correct. Okay, because 1.6 times 10 to the power of minus 19 is the elementary charge. So we expect it to be the smallest charge, not going below it. And last question, the nuclide magnesium is an isotope of magnesium that undergoes beta plus decay. So beta plus is 0, positive 1. To form a new nuclide X according to the equation. When I try to balance the equation, this will be 23 and this should be 11. So that proton number on both sides is 12. 4 numbers are missing from the equation. I've finished to add the numbers. For the nuclide, state what is represented by the number 23. 23 is of course nucleon number. And then 12, that is proton number. Complete the equation by inserting the missing numbers. I think I've already inserted the missing numbers. Just balance the proton number and balance the nucleon number. State the name of the group of fundamental particles to which the positron and the neutrino belong. These ones are leptons. Then a radioactive source emits particles from its nuclei when it decays. The figure shows this, for the source the variation with the kinetic energy of the particles emitted. We see that as the number of particles emitted increases, they have the same kinetic energy. That's why the graph is vertical. These particles are most likely going to be alpha particles. They cannot be beta particles because beta particles have a range of kinetic energies. State how the figure shows that these nuclei do not undergo beta decay. So we see that the emitted particles, have a single kinetic energy. The emitted particles have a single kinetic energy, yet we know that beta decay results in a continuous range of kinetic energy. Yet beta decay would result in a continuous range of kinetic energies. Okay, if they were to be beta particles, the graph would show continuous range of kinetic energies. But since the graph is showing a single kinetic energy, it is constant, it means these are not beta particles, so it is not a beta decay. I think that marks the end of this paper. I try to be faster, and see you in paper 4.1 and paper 4.2. Bye bye.